The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Okay, hello, good afternoon, everyone. Welcome to today's webinar in our Discovery series on AI for Earth and Sustainable Science. I'm Maria Piles from University of Valencia, and this seminar series is curated by the ELIS unit in Jena and the ELIS program on machine learning for climate and earth system science. ELIS is an excellence network, European excellence network on AI, learning and intelligent systems. This is one initiative that we have in collaboration with ITU, and it's my colleague Gustavo Camps Weiss from University of Valencia, and then we have also Markus Reinstein and Joachim Denzler from Max Planck Institute of Biogeochemistry in Jena. So we are the four of us moderating the series. So today I have the pleasure of having with us like Ingmar Nitzel from the Alfred Wegener Institute for Polar and Marine Research in Potsdam, Germany. And he will be presenting a talk about tracking permafrost landscape dynamics in a rapidly warming Arctic. So thank you for coming, Ingmar. I have a brief CV here. It's like you're a postdoctoral researcher in the permafrost research section, so specific about permafrost at the Institute for Polar and Marine Research in Potsdam, Germany. Your background is in geography and remote sensing, with a strong focus on technical applications. So you will show us directly applications of machine learning, deep learning techniques on spatial and Earth observation data at various spatial and temporal scales. So Ingmar focuses on quantifying, understanding, and predicting rapid landscape dynamics and disturbances with focus on terrestrial Arctic environments. And he just told me he's actually very close to the Arctic, not in Potsdam. So, so you're very close to your research field, like live. Okay, so do you want to add any other thing to your CV? Otherwise, the floor is yours, Ingmar. Thank you.
Okay, thanks, Maria, for the nice introduction. And of course, first of all, I would like to thank the organizers for inviting me for this talk and kind of bringing you closer to the world of permafrost, to AI research, and yeah, over the next 40 minutes or so, I think you will learn a little bit. And yeah, permafrost. So permafrost is quite special, right? So I'm in this field now for almost 10 years. And And yeah, I'm working there in several research projects, which of course from Yavi, but also in the Permafrost Discovery Gateway, which was a big permafrost project. And currently I'm working in the Google.org Impact Challenge Permafrost AI project. So there's a lot of support from that side as well. And yeah, let's start here with permafrost, about the talk tracking permafrost landscape dynamics in a rapidly warming Arctic. So this photo was one of my first impressions when I kind of came into that field. So this is an erosion feature in the Arctic, which will be kind of the main feature I will talk about over the next half hour or so. This is called a retrogressive thaw slump. So there we see erosion, which is caused by melt of ground ice. And people typically think of the Arctic as glaciers, or think permafrost, okay, has something to do with glaciers. It doesn't. So you'll see about that. So actually this photo was shot in northeastern Siberia during my first expedition in 2014 as a young PhD student, and kind of was my first really real impression of that. So little bit about me. So I was introduced very nicely a little bit, but yeah, I see myself. So I'm let's say real geographer. I like to tap into different fields, into all of them. So that's kind of really my passion. I also love remote sensing, so Earth observation with satellite and aerial images, for example. I like visualization and computer stuff, and all that kind of shaped my career path to some extent. And yeah, what I also love is exploring. So tapping into new fields, discovering new things that haven't been discovered before. And permafrost is a real good topic for that, because everything's so remote. You're so far from many places. So there are really white spots on the map, right? And I would describe myself as kind of a sandbox scientist. So I love experimenting, playing around, like using all the tools that are out there in terms of remote sensing, in terms of AI, to kind of put them together like in a sandbox, right? Or with Lego. So that there are so many great tools. So I can really explore that and have fun with that. And I kind of, my background is, I come from Germany. I studied in Berlin, Potsdam. Then yeah, went over to University College Cork in Ireland, which was quite a good experience. And in 2014, I actually kind of got the first time in touch with permafrost, which is kind of an exotic topic, but which becomes more and more mainstream, which becomes more and more important, especially in the kind of, let's say, issues with climate change that we have. So it's becoming a bigger and bigger topic. And yeah, I started as a PhD student at AVI, and somehow could stay at AVI even until now. I love doing the computer stuff, but I also do field work. So I did land expeditions in the Lena Delta in Siberia. Started pretty much in 2014. Did some more in Alaska in 15 and 16. And since then, I kind of yeah, moved into kind of a lot of aerial imaging campaigns. So at AVI, we have two airplanes where we can put a lot of tech in there. So we can do laser scanners and cameras and different scanning systems. And I've participated in 4 campaigns in Alaska and Canada, and we will have another one in Alaska this summer. So this is a little bit broadly about me, to just get a feeling, okay, where I come from, what I've been doing, kind of what is the fun of working on that topic. Okay, of course we're talking about permafrost. It's not super well known to many people. So permafrost actually has a very simple definition. It's just frozen ground. So the let's say hard definition is ground that stays below 0 degrees Celsius for 2 consecutive years. So it's just a physical state. It's just temperature of the ground. You know, the Arctic is typically quite cold. So permafrost affects really large areas. So 14 to 24% of the northern hemispheric landmass, depending a little bit what kind of sources you take. But really, I think the latest numbers are about 14% are really frozen ground. So the soils are frozen year round. And why it's important is that it's a massive carbon storage, right? So we have a lot of carbon stored there that was deposited there over thousands of years, especially during the last ice ages. So during the last ice ages, many of these areas that we see here in blue on this map, which is permafrost, weren't even glaciated. So most people think of glaciers in the Arctic, but there are a lot of unglaciated areas. But there's a lot of carbon stored in the ground, and once that thaws, think of some food that you have in the freezer. What happens if you put it out there? It just thaws, right? There's a lot of, and it thaws, it rots, it starts to stink, and the carbon that's stored in there kind of can go to the atmosphere, and the same thing can happen with permafrost. So we have a lot of plant remains that were stored there over thousands of years, but also animal remains. So, and all these kind of stay there. And if we think of the proportions in permafrost soils, we have around double the amount of carbon stored in permafrost compared to the atmosphere. So think of that. If even a fraction of that goes to the atmosphere, that poses, yeah, let's say strong problems. So we have this kind of feedback loop. So once we have more carbon in the atmosphere, we have more warming, etc. And then it's kind of a positive feedback loop that enhances this process. So it has an influence on the global climate. So often there's the question, like, why do you do permafrost research in Germany, for example? You don't have permafrost, right? So, but what happens in the Arctic does not necessarily stay there. So it has global implications. What's interesting in permafrost, we think of, oh, okay, it's cold, nothing happens, but it's actually not true. So it's a really dynamic landscape, which you will learn about a little bit later in this talk. And it's vastly understudied, I'd say. So it's very sparsely populated, and historically, yeah, people did research where things are accessible. But yeah, in the Arctic, field work, for example, is pretty tough. But even remote sensing can be quite challenging in certain areas. So that's kind of the main significance of permafrost. Okay, what does permafrost look like? I said, like, the definition of permafrost, it's basically frozen ground or cold ground. But we cannot really measure that from the top, right? So what we see here is the tundra environment in the Lena Delta. But that could be also some grass, right? But we know that there's sparse vegetation, but we don't know what it looks below the ground. So for that, we have to take indirect measurements or dig into the ground, take soil cores or something to really know that. But from space, we cannot really measure it. And what exactly this place looks like from the ground, we can see in exposures. So for example, this is quite spectacular, one of the most spectacular places I think that there are that we have for permafrost. So this is the Sobosisa cliff in the Lena Delta, which is, well, for research, not really accessible anymore for obvious reasons. But this was taken in 2014. And here we see an exposure of a specific type of permafrost, which is called Jedoma, which is very ice rich. So you see here these bright gray things. This is really ice. So these are ice wedges, which are very distinct for permafrost. So ice wedges form due to the contraction and cracking of the ground. So once in winter it gets cold, the ground just contracts, forms little cracks, and that happens every year. And then these ice wedges can grow. So in this cliff, we have around 70% ice content. And once the ice melts or the permafrost thaws, that can kind of, leads to issues. And all the black stuff here is frozen soil. So there is a lot of peat and carbon in there. And once that thaws, that either goes to the water or even to the atmosphere, which then enhances global warming. And kind of monitoring the fate of permafrost is quite essential. And also, this can also be permafrost. So this is a soil core, which we took with an big drill. So there's also in these in a lot of permafrost soils, we have a lot of ice, and that's very vulnerable towards warm temperatures or contact with water. So water and warm temperatures are not good for permafrost. So the problem is in the Arctic, we have something called Arctic amplification. And as I said, well, warm temperatures are not good for permafrost, and also water and moisture and precipitation are also not really good. And what we see in the Arctic, so on the left-hand side, we see the warming. On the top, we see temperature changes. So the darker red, the more warming we have. And we see that the Arctic is the place where we have the strongest warming globally. So once we talk about, let's say, 2 degrees warming globally, which is kind of one let's say popular number that's always named, we talk about 5 to 6 degrees in the Arctic. So there's kind of a 3 times more warming in the Arctic, and that kind of can lead to bigger issues. And the same with precipitation. So with more warming, we also have more precipitation, and both of these are not really good for permafrost. So that this is kind of actually a bad combination, right? And then we have this feedback loop. So once we have more warming, we have more thawing, more carbon emissions, and that is kind of a vicious cycle, which we, let's say, try to quantify and of course try to minimize, hopefully. Okay, what happens in permafrost? What are the landscape dynamics? This is kind of a, let's say, quite spectacular schematic of the different processes, and especially erosion and degradation processes that we have in permafrost. So we have, for example, these here for number 4, we have these ice wedges, which are quite typical. So this is pattern ground. There's a lot of ice stored in the ground. We see a lot of degradation of these features, which is caused by warming and wetting. So this kind of also leads to permafrost thaw, to changes in hydrology, to changes in the carbon cycling, water cycling. What we also see are wildfires. The permafrost zone spans the boreal zone, so a lot of forested areas, which are becoming more vulnerable to wildfires, which then in turn disturb the ground and lead to more permafrost degradation. But we also have a lot of erosion forms, which we call here hill slope thermokarst. This here in number 7. So these are called retrogressive thaw slumps, which are, let's say, pretty obvious features of degradation of the permafrost. And these are kind of the main objects we're looking at for tracking. Okay, so as I said before, permafrost landscape dynamics, or there are permafrost landscape dynamics. The thing is, permafrost cannot be directly measured from space, as it's just the temperature. But what we can do is to monitor the state of permafrost is observe the dynamics of the permafrost, which give us an indication of the ground conditions. So certain landscape dynamics occur in, let's say, certain ground conditions and certain temperature ranges and certain stability ranges. So the more permafrost degradation we have, the more and more enhanced dynamics we can expect. So we use disturbances and dynamics as proxies of the state of permafrost. And 2 of the, let's say, most obvious targets that, particularly in my work and in our group's work, are lake changes, which we see here on the left. So lakes in permafrost are typically very dynamic, so they interact with the frozen ground. So once you have a water body that can store water or heat in summer, and if it's deep enough also in winter, that interacts and thaws into the surrounding permafrost, and we can measure that. And there's a typical life cycle for these. So they can form once there is some disturbance. Then they form ponds, and the ponds, they grow bigger, and at one stage they might drain or just merge with other lakes. So and the other ones are especially erosion, where we focus here on retrogressive thaw slumps. So on the right-hand side, you see an aerial image that we took last year from a large retrogressive thaw slumps, which are kind of landslide-like erosion features, which we have in certain areas in the Arctic, and which are popping up at some unprecedented velocity, I'd say, at least in some areas. So here in this presentation, we focus quite strongly on these features. Okay, this is also a nice oblique aerial image from the Selawik slump in Western Alaska, taken during one of our campaigns. So we see so these features are formed by melting of massive ground ice. So let's think of glacial ice. So during the last ice age, in some places, there are still some moraines of these glaciers, and there's still ice preserved in the ground. And these are big ice blocks, but once they kind of get some heat pulse in warm summers or due to running water or something, they start to melt, and then they collapse, and then they can form these big landforms, and they expand. So here we see these orange arrows. So typically they start a bit smaller, and then these features can expand over time, which you see in the results later, and that produces it's called scar zone here in the middle, and the sediment gets washed down, which has sometimes quite strong implications on the water quality of the rivers or lakes, which are often used by as water resources for fish or even for people living in the vicinity. So here is an example again of this big thaw slump that I showed you before. So we try to track them with Earth observation data, so in specific with satellite data or aerial images. So here's a nice example of an imaging campaign last year where we flew over a lot of thaw slumps in northwestern Canada. We use multispectral data. That means that we have here on the left-hand side, we see the let's say a camera that takes images in the visual, like a visual image, like we see it with our human eye. It's called RGB, or true color. So this looks from the top, but we also have different other spectral wavelengths in the near infrared, which has a strong contrast in vegetation. So in the panel B here, for example, you see in bright there are areas with stronger vegetation, and in dark with less vegetation and like muddy surface. So we can have a distinction between the undisturbed vegetation part around and the dark unvegetated mud pool, I'd call it here, where we have the active part of the thaw slump. And with the cool thing with our aerial images, we also have thermal bands. So we see here in blue the actively exposed permafrost or frozen ground, which is really cold, which pops up nicely in the thermal imagery. So we can use the strengths of these different wavelengths that the sensors have to identify certain parts of these thaw slumps and map them nicely. Okay, so we want to really map them across big areas. So their significance lies in that they're a strong permafrost disturbance. They have influence on biogeochemical cycles, as I said before. So they can release carbon to some extent, but they also have a strong influence on water quality downstream. So they also can form issues for water users downstream. They're a geohazard, so there's some hazard around them. as I said, downstream ecology, and they are a strong indicator of change. So we expect to have more dynamics, stronger dynamics, as kind of an indicator for the changes that we see in the Arctic right now. And I guess in the future, we will also see even stronger changes. And to target them and to track them, we need to kind of look for certain attributes. So they have a certain size and shape. So they typically kind of come in this roundish form, but along coast, they can also have a more elongated shape, which then helps us to target them better with AI methods. They are dependent on certain stratigraphy, so we need a very ice-rich ground, which was formed by certain due to certain conditions, which I go into detail. We have distinct vegetation patterns, so typically they are surrounded by some kind of vegetation, and the features themselves are mostly non-vegetated. So that helps us to distinguish them from surroundings. They have certain dynamics, so typically they are dynamic in time. But sometimes it's tricky to say, okay, which parts still belong to the thaw slump and not. There's still ongoing discussions how to name certain features. So sometimes definition is not 100% clear for certain parts, which makes it really tricky to communicate between different groups and to talk the same language. And the issue is there's no real pan-Arctic inventory available yet. So we have good information in certain areas where there is a lot of field work going on, and also some groups have a very strong regional focus, like in northwestern Canada. They're quite nicely mapped, but not across the entire Arctic. There are first data sets that are going that direction, but I think we're not there yet 100%. So that's what we are kind of working on, right? Okay, this is a nice little video of one of a small thaw slump in Western Alaska that you just get a better look. I hope the video is okay over your Zoom presentation. So we see here nicely the head wall, which is the active erosion zone, where we have right like a proper steep wall where it's typically actively eroding and expanding over time. And here's the debris lobe. So there's a lot of sediment being washed downwards, and here in this case into the sea in Western Alaska. So this was taken by drone flight of one of our field campaigns in 21. Okay, let's go to the distribution, spatial distribution, because thaw slumps, there are maybe tens of thousands of thaw slumps across the Arctic, but the Arctic is very large. So it's kind of a needle in the haystack problem, but they are not randomly distributed. So they follow certain distributions because they can only happen in certain environmental conditions. So they are a slope process, right? Like landslides only happen in slope terrain. Same for thaw slumps, which we here call RTS, retrogressive thaw slumps for short. They need some massive ground ice, which can be formed by moraines. So typically they happen in formerly glaciated terminal areas, so where the glacier kind of had its maximum extent for a while. Where there are some buried ice of the glaciers, which in a cold environment could sustain there and is now kind of starting to melt. So this is kind of one of the main locations of thaw slumps. We also have marine sediments where we have very ice-rich conditions and maybe also salt. So salt lowers the melting point. So even in salty sediments, it does not melt at 0 degrees, but even colder conditions. Then we also have Jedoma ice-rich permafrost, which we saw this big cliff at the beginning. So that's also one one type where we can expect that. And we also need trigger mechanisms. So they are typically formed by lakes. So thaw slumps typically happen around lakes or rivers or coasts. So in combination with water, we can at least confine our search or focus our search to certain areas. So this all leads that they're kind of clustered and happen in certain areas. So here we see, for example, in northwestern Canada, nice study by the group around Steve Cookay. We're really doing a lot of inventories in that area and doing cool work. So we see here, it's called Banks Island, this big island. I hope you see my mouse. If not, I try to explain. So here on the top of panel D, on the east coast, there is kind of a big terminal moraine of the last major glaciation in North America, and also in the Peel Plateau, which is on the really western margin, west of this little marked Inuvik, town of Inuvik, where we have also this aerial image from where I showed you the panel before of the different wavelengths. Okay, so now we come to the remote sensing AI part. So much for permafrost. So here we see, so we really want to focus on our targets, which are retrogressive thaw slumps. Maybe it's a little bit hard to see, but that's the problem, right? So thaw slumps are really hard to track, even when we know they are there. This is an example of a time series of images from the Taimyr Peninsula in northern Siberia. There are also a lot of thaw slumps. And here in yellow, we mark them, their extent in 2016. And then the second image is 2017, where we see very, very little expansion. And in 2019, we see already these dark margins expanding. So the yellow line represents the 2016 extent. So what we see here is multispectral images. So it's not the real colors that we see with the eyes, but with vegetation enhanced in red. So we see here the near infrared information in red. So what we look for mapping thaw slumps is vegetation versus non-vegetation. So our main properties we're looking for are erosion, so a lack of vegetation typically. So we look for muddy surfaces. We look for areas that are changing. They are typically quite small, from a few square meters to a maximum of 1 or 2 square kilometers. So that's quite small if we're thinking about millions of square kilometers across the Arctic. The problem is they often remain undetected. So many of them are just not known. They're clustered and they are progressive. What we see here that they're expanding, but they can also polycyclic. That means they have active phases where they're expanding, then they're kind of becoming dormant. So they are not becoming, or they're becoming inactive. So they grow over with vegetation, and then the process starts again. So it can be quite complicated and complex. And for mapping them, in terms of terminology for image analysis and AI, we have a segmentation problem. So we want to find the footprints of them. So what kind of footprint they are covering. We could also go for just identification. So having a location where they happen. What we also need, due to the small area that they're covering, is we need a high spatial resolution. So pixel size as small as possible, but also good temporal resolution. So we want to monitor the temporal dynamics. And to put that into a bigger scope, what we want to do is we start with Earth observation data, which we see here on the left. So this is a nice example of one of the biggest thaw slumps in the world on Banks Island. So this is also a multispectral image. We see here this bright area is the thaw slump in the middle. So we want to understand and map the landscape processes. So how big they are, how fast they are, etc. But we do not just of course, it's fun. So for me, that's definitely fun, but we do not do that only for fun, right? So it has to serve a purpose. So we really want to understand the spatial temporal dynamics and retrieve the drivers of landscape dynamics to really understand and model the future and see, okay, what are the consequences of these things, right? So then these data will be fed into bigger landscape models, which then can predict what will happen in the future. For example, how much additional carbon will go into the atmosphere, to then better understand, okay, how much more warming will we have with these enhanced dynamics of the landscapes. Okay, so for segmentation, for detection of thaw slumps with AI models, so we're using AI models where we're trying to detect them, to map them. We need training data, we need labels, right? So we need to provide the models input data, but also we give the models examples. What are thaw slumps, where they are located, what do they look like? And this is a nice little selection of 6 different sites in across the Arctic, where we have information on thaw slumps. And the problem with thaw slumps is the landscapes they are sitting in are super variable. So it can be really tricky. So these are, again, false color composites of satellite images. So again, here we see in red vegetation areas with vegetation, and for example, here with these black outlines, we see the thaw slumps that we mapped. And even with a bare eye, they are sometimes hard to distinguish. So here on the top left, this is the coastal site in northwestern Russia. It's in Kolguyev, for example. So they typically are located around water bodies, which helps. So the models can kind of understand, okay, thaw slumps or some areas which are not vegetated close to water bodies are likely thaw slumps. That helps. But still the landscapes are super, super variable, super different. So they can happen from, let's say, 65 degrees north to maybe 80 degrees north, which is a really, really large span with different types of landscapes. So here on top left, we have Kolguyev, which is an island in northwestern Russia. We have in the top middle, it's on Banks Island in northwestern Canada. On the top right, we have some close to the Lena River in Siberia, and on the bottom we have, I think, in northwestern Canada, in the Tuktoyaktuk Peninsula area, on Herschel Island in the middle, which is also quite prominent, and another one in northwestern Canada, which is Horton, close to the Horton Delta, which is quite special. But we see the different kind of types that we see there, and kind of putting that into one, let's say, big detection model can be quite challenging, right? So the variation of landscapes is the biggest challenge, or one of the biggest challenge, and also different shapes and sizes and what they come in. Okay, what we used for one of our specific analyses is, so we use satellite data, in this case, multispectral planet data, which is 3-meter pixel resolution. So 1 pixel is 3 meter in size. Planet has a constellation of, I think now it's almost 200 satellites in orbit. So we have a very high temporal resolution, but it's commercial data. But we have a, let's say, quite extended license, but it's not unlimited. There we use the multispectral data. So we have 4 bands, so in blue, green, red, and near infrared. We calculate vegetation index, which we see on the right at B. So where we have already a distinction of high vegetation versus low vegetation, which is a good indicator. So that helps, definitely adding that. So this is kind of a feature engineering approach, I'd say, in more technical terms. Then we have an auxiliary data set. So this is based on Landsat data, where we have long time series but low spatial resolution, where I'm kind of calculating trends over time. So we typically look at single individual images, but here we add a temporal component. So we have some time series information, but on a lower spatial resolution. What we have in the Arctic is, in terms of elevation models, is pretty good. So it's called the Arctic DM, the Arctic Digital Elevation Model, where we have in pretty high resolution information on elevation, but also derived data. So from an elevation model, we can also calculate kind of a relative elevation. So which elevation has a point in relation to its neighbors or 100 meters away. So this kind of gives us a good information on the slope. So how steep is the slope in a certain area in a very high resolution, which definitely helps to map these morphological features. And we add a lot of training data, which we have hand drawn across large regions. But there we also have the problem, okay, which parts belong to the thaw slump, which not? And we even conducted an experiment among real experts of thaw slumps, and even there was not a real good consensus in some areas. So that's still kind of, this is an additional layer of complexity, which makes it tough to really define the features we want to look at. And as an output, we create geospatial data products in raster format. So this is kind of a, in the same shape of the satellite image, but also vectors. So polygon vectors, which give us a spatial representation of the footprint of thaw slumps at a certain point in time when the satellite image was shot. And of course, we only look at summer images. So in the Arctic, we have the challenge that we only can, or for this purpose, we only use summer images where there's no snow on the ground. So most often talking to people about permafrost, people think that, okay, permafrost, it's always ice, it's always snow, even in summer, but it's not. So these are typically continent or land areas, and they can become quite warm. So even last year when we went to Canada, we had more than 30 degrees north of the Arctic Circle. So it can even become quite warm. Okay, so we also published on that, testing our methods in different areas. And as I said before, the locations, the regions, or the landscapes can be pretty different. So what we tested for was, so we trained different deep learning models, and we used convolutional neural networks, they're called. They're pretty standard for image segmentation, so finding certain polygons or detecting certain objects. So there we use different architectures that they're out there. For example, UNet is one of the most prominent examples of that. We did kind of proper quantitative assessment, so really rigorously tested for its accuracy. And we specifically tested for transferability of the model. So we trained in 5 regions and validated in a 6th regions to see, okay, if we train it in certain parts of the Arctic, if it still works if we apply it in another region, because we will never have, or let's say it would be very much work and would take a lot of time to create training data across the Arctic. So that's kind of always the thing with supervised or deep learning models, right? That you never or rarely have enough training data that your model will perform perfect. So this is kind of, we see here on the top left, like this is what a satellite image, the input looks like. And on the top right, what kind of the model would give us as a result. So we see here in red that the model says, okay, this is a very high likelihood that these are thaw slumps. So this is kind of what we get for for each image that we feed into our models. And we had certain let's say good results. For example, UNet++ is a good model for that. The transferability is pretty variable, so it really depends where you train your data to get good or better or worse results. And yeah, having standardized Pan-Arctic training data would be required for upscaling. But there are some groups working on that. So my colleague, for example, Yili Yang from Woodwell Research Center, he's kind of trying or he is building up kind of a training database which spans really large areas. And there we also have some community efforts to bring that together, to join forces, and to make things better, and to learn, and to improve the outputs. Okay, here are some examples. So on the back, you see the Esri satellite layer, which is a very high resolution data set, which is just for visualization purposes. And the lines that come in and out here are our model outputs. So the top left here is on the Peel Plateau. This is the area where we also had the aerial images from, right? Taken from our airplane. And there we see in white colors from 2018, with more reddish becoming in 2021. So this is kind of a time series. And we already see that there's some progression of the thaw slumps, which follow our kind of the theoretical understanding, right? So I don't know if you see my mouse, but I explain it. So on the northwestern part here, we see a nice expansion over time over this period of 4 years by maybe around 100 meters. So this gives us a good information. Okay, how are these features evolving? And these are just very few of several, I guess, tens of thousands across the Arctic. And we see the same on the right-hand side in Novaya Zemlya, which is kind of this elongated archipelago north of the Ural Mountains in northwestern Russia, which is one of the most dynamic places where we have thaw slumps, which is super interesting. So what we see here that in well-known regions we have good performance, but the models do not always perform perfectly because it's a really tough task. But what we also see is the temporal evolution, which is good. So because we really also want this temporal information, and we see the well-defined head wall. So the head wall is the part where we have the active erosion, which is very distinct, where we have a very steep wall, which is nicely detected. So which makes us pretty happy. Okay, this is kind of a regional output. So on the left-hand side, you've seen that image before, right? So this is the map from Kokay, where we have in this panel the distribution of thaw slumps. And on the right-hand side, maybe it's a little bit hard to see. I hope the resolution is fine enough that you see these little dots are our outputs in different colors, different years, but the color here is not super important, but more the spatial distribution. And to make it a lot clearer, so these are the raw output vectors, but the spatial patterns match quite well. And if we run over a certain kind of density estimation, which we did here with a kernel density estimation, is just kind of a spatial statistical analysis, which gives us the density of thaw slumps. So in deep red, we have a higher density of thaw slumps, which kind of matches the patterns of the manual mapping and other data sets quite well. So we are kind of getting there and can get at least the spatial patterns that were observed with high resolution and manual mapping. So we're quite happy with that, and we also have that for large regions of Siberia as well. And we're really aiming for Pan-Arctic analysis, where the model runs automatically, and within our Google Permafrost AI project, we're really kind of trying to make leverage of big infrastructure and big processing infrastructure to really make that systematic and kind of have a monitoring of our analysis. Okay, there are pretty good ones, right? So it's always nice to show the good stuff, but of course there are issues, right? We have good performance in trained areas, so where we have training labels, where the model really knows the region. It's really fast, right? So the training of AI models is typically very tricky or very, let's say, takes a lot of resources. So you need a lot of GPU processing power. But it's called inference, the application of the model, and then creating some output is typically pretty fast. So that works quite nicely, but we have still a lot of challenges, right? So we have many false positives. So the model thinks, especially in areas where there's just background, but no active erosion, thinks that these are thaw slumps. Then there are some, especially background around water bodies, which we see here on the top. There's the river, and there's some background around the rivers that the model thinks these are thaw slumps. So that's tricky. Then we also have the problem, okay, what is a thaw slump? If that's not really clear, what part should we map as a thaw slump? Makes it also a bit tricky. And of course, data access. So here in this example, we are using planet scope data, but they're commercial data, right? So we have to pay for them, or let's say the access is restricted. And adding or using free of charge data or freely accessible data like Sentinel-2 from the European Copernicus mission, but they have a lower spatial resolution, which comes with some drawbacks, but they're more easily accessible. So we're trying to kind of put that together, or trying to go different directions, or testing different directions, what's possible. So what we're also working on is called self-supervised learning. These are kind of a little bit more advanced methods which can handle data where we have little training data. So these models self-optimize itself. They kind of have better learnings, have internal learning strategies where they think, okay, these data or where we're just optimized better. So my colleague Konrad Heidler is working on that, and which already gives us better results. We're also using additional data sources like Sentinel-2, which are freely accessible, but have a lower spatial resolution. But there it's easier to have a panarctic extent and do some monitoring. And of course, for now, we're just using two-dimensional data, but these are, of course, morphological features that are three-dimensional, right? So it's also very important how much volume changes we have, right? And to better understand, okay, how much carbon, for example, was released by the erosion features. Okay, let's come to some topics that are not thaw slumps. So here I would love to feature one really nice application of a colleague of mine, which is super awesome. So here we see a nice aerial image of a coastal region in northern Alaska, and what we see here are ice wedge polygons. So I hope you see this polygonal patterned ground, which is very typical for permafrost. So we find that in ice-rich permafrost, and which is a good indicator of the ice content of the ground. So that gets formed by contraction of the ground. Just think of shock frosting something. So it contracts due to the cold. Then we have little cracks that fill with meltwater of the snow in the next spring. That freezes, and then that happens over tens, hundreds, thousands of years. That forms these polygonal ground, and we have. And nobody knew how many of these features we have. And my colleague Chandi Vitharana from Connecticut was also mapping them with deep learning. So similar method like the thaw slumps, maybe even, or let's say a lot of data, right? So we have 3 million square kilometers, produce a data set of the footprint of these ice wedges. So they used over 30,000 maxar scenes, which is the highest spatial resolution we have, data we have for commercial data. So it's, I think they used in 50 centimeter pixel resolution and 250 terabytes of image data, and mapped these ice wedge polygons around the Arctic. And the data set is available and visible, and also you can visualize that in the permafrost discovery gateway data portal. So there's a viewer where you can really look at this data set and look for these polygons. Here on the right, you also see a nice image of them. And there are a lot of additional data, like the type, centroid area, perimeter, the different directions, trough widths, etc. So also the type of polygons, so the stage, if they're degraded or not degraded. So this is I'd say the biggest data set I think in permafrost research that we have. Then another nice little side project of myself. This is kind of a topic I slipped into where some colleagues asked me to help out, because I'm typically, or in the past, I did a lot of mapping of general landscape dynamics across the Arctic. And there are some animals that are shaping the landscape in some places pretty strongly. And they are beavers. So beavers are moving northwards. So we have warming, we have more vegetation, we have shrubification. So the beavers follow suit. And we see in a lot of areas in Alaska and Canada that beavers are migrating northwards, and they're reshaping the landscapes. They're changing some water cycles. They're damming up lakes, which also then has implications on the permafrost. As we know, water and permafrost are not good friends. This is kind of, well, at AVI, we also have these aerial imaging campaigns, which I said at the beginning. So I kind of participated in a lot of these campaigns over the past years. And we also acquired maybe 1 million aerial images or so. And so I just created a little detection model for finding beaver dams and beaver lodges. So we see here an aerial image, like the big one. The arrow points towards a beaver dam, but we also have a beaver lodge here. And on the bottom right, we see this beaver dam that's indicated. And on top right, there's our plane, the Polar 5, but we also have the Polar 6. And this is pretty cool. So I trained a object detection model for those who are interested in that. It's based on YOLO V8. It's quite lightweight, and you can use it yourself. Maybe I can. I don't have the link to the model here, but it's public, and you can just feed in an aerial image where you think you have beaver dam, and then the model tells you if there's a beaver dam or not. It's not perfect. It doesn't really work perfectly, but it still finds a lot of beaver dams that maybe even with a bare eye we wouldn't recognize that quickly. And here we see the example how that looks, how the output looks like with the beaver dam, the confidence of the model, and the beaver lodge that got detected here. Okay, there are other cool data sets and stuff that I've worked on are lake changes. So this is an image of lake changes that we see across the Arctic. They're a bit or enhanced, let's say, visually. But we see areas in blue, for example, where we have expansion of water, especially in inland areas where it's important, or red, where we have a loss of lake area. So we see in some areas in Alaska, Canada, Siberia, that we have quite a lot of lake drainage recently over the past years, which is perhaps due to climatic changes or degradation of the permafrost. So, for example, here in this northern coast of Alaska, we see different landscape units which have different ground conditions. Along the coast, we have expansion of lakes, and a little bit further inland, we have more loss of lake area, for example, or in Western Alaska. Yeah.
Sorry, we're close to 1 hour, and then
Okay.
we have some debate. If you can just go to the
Yep,
conclusion.
I'm almost finished.
Okay, thank you.
Okay, perfect. Okay, and yeah, that's what it also looks like for individual images. So we mapped around 6 million lakes, and where we can see, okay, lakes are expanding, lakes are shrinking, and then basically try to find out the underlying processes and the main influence factors to really understand how lakes will change in the future under future climate scenarios. Okay, and with that nice little sunset image from my first expedition, I would like to thank you for attendance. And it took longer than I expected, so I was talking a little bit more. Yeah, you will find all my information. You can contact me at any time if you like. Just send me an email, contact me, check my GitHub. And yeah, I'll thank you for having me, inviting me, and yeah, really now open for question. Really looking forward for your questions. Thank you.
Okay, thank you. Thank you very much, Ingmar. Okay, here we are. So so we have about 10 minutes for questions. So I have many notes and I'm very curious about many things. It was a really good intro to the Arctic landscape and all the phenomena. I learned about these ice wedge polygons in the thaw slumps. Okay, very, very interesting. Perhaps if there's no questions, so to the audience, you can just type your questions and then we will bring them here. But in the meantime, I can just ask myself. So I'm very curious about, in particular, the temporal resolution of the phenomena, because you didn't show any time series. So, and you say that you need good temporal resolution. What is good for capturing these processes?
Depends really on the region. Ideally, of course, if we have once per week, which would be good. At least once per year, I'd say. So typically these changes happen in the summer season, which depends where you are. For the north and the Arctic, it's shorter. For the south, it's longer because the summer is longer. But ideally, at least monthly would be good to really see, okay, what is the impact? Especially, we for thaw slumps, the problem is we have knowledge for a few sites only, but we don't have any statistics across the Arctic. And to really understand the main impact, the main drivers of these changes, we need good statistics. And ideally, of course, we would have daily data, but weekly, monthly would be also good for now. But that depends a little bit on the area. If it's in some places it's lower, the resolution can be lower, right? So the spacing can be longer. For regions where we have a lot of change, then of course for a good quantification would be good to have denser time series.
So in your exercise or in your results, when you were tracking this, identifying, classifying thaw slumps, were you using the temporal signature or the planet images, or were you just or were you actually using the evolution, or just putting them the different images with the labels?
At the moment, it's just single timestamps. It's really just image, but we're kind of working on also kind of have this temporal signal. I mean, there are a lot of like techniques coming in with transformers and kind of which are more time knowledgeable, let's say, to have these kind of as new methods would be super great to put in there, because I think that would be a big boost, because for now it's kind of let's say a little bit stupid, right? With it's not taking time into account, but that of course would be a big step add and
So
boost the
also because
quality.
I understand the labeling is difficult, but then once you label it, if you can exploit, that place a long time across time, it would be beneficial. So I guess I think that would be a very good angle, no, to put into the model the information. Okay.
Yeah, definitely.
And then about remote sensing, I've worked a lot with microwaves. But then you're not using microwaves, but then perhaps it would be interesting to look at, there's a lot of sensitivity in the L1, for instance, to the freeze and the thaw processes. So perhaps, there's also sensitivity to the land surface temperature. So this would be an interesting signal coming out. Problem perhaps is that L1 is typically having coarse resolution. So you're talking about meter scales. With Planet, you have 3 meters. But there's later this year, there will be the nicer mission. It will have an L1 radar with 5 to 10 meters. So perhaps that's a good venue to try to use the data. Have you considered it? Or
I mean, in the Arctic, I guess, also with clouds and sun angle and all these issues that we have with optical data, of course, SAR data are used. Not for this application, more for water applications. It's quite a lot in ice applications. So their SAR data are very popular, but for, let's say, high resolution geomorphology mapping, not that much. So I also have a colleague who are kind of using it more indirectly with tandem X data for 3-dimensional changes. So having kind of differential DEMs, etc. So more indirect way, but would be interesting to see if we can look at thaw slumps if, well, there are not too many negative influence factors like with all soil moisture and all that stuff. But I think bringing in multiple sources would be, of course, great.
once you have the labels in place, you can go and get the data.
Yeah, sure. But then, of course, you need it for a certain timestamp, the labels, and because they at the moment they have a certain timestamp because they're dynamic, right? So, but there's still certain, let's say, wiggle room to or a certain period where we can use the labels.
No, I'm just thinking that the knowledge of whether the soil is frozen or not should be important. And the thaw, so with the freeze thaw product, you can just see the transitions and go there at that specific perhaps. Okay. And then I think, we have very little time, but just one broad question. You focus on the Arctic, but what about the Antarctic? Is there is it important to quantify these processes out there? Is there an Antarctic amplification or?
So in the Antarctic, so the glacial processes are definitely more dominant than in the Arctic because the ice sheet is so dominant, but there is permafrost research in Antarctica, so especially around the Antarctic Peninsula. So there are colleagues, especially from Portugal, who are working on that. But for thaw slumps, I haven't heard of anything. There might be some, but there are different processes there. It's not that much carbon. It's a different landscape. But there are certainly some permafrost research, but not as much. So permafrost is really dominated. Let's say for lowland permafrost in the Arctic, but there's also permafrost in high mountain areas. But there the processes are different. So it's really, really diverse. So there are a lot of people also working in high mountains like the Alps, Andes, in Asia. There are a lot of processes also there, but they're quite different.
Okay, makes sense. We have one question from the audience. It's from Umberto Fracassi. He says, thank you very much, Ingmar, for the very informative webinar. And then he asks if is ground deformation subsequent on thawing expected to occur in a systematically quasi-polygonal pattern, as in the image you showed, or does it occur in a more structurally complex fashion or distribution?
So in terms of thaw slumps, it's hard to predict, right? So some are more in a continuous fashion, but we also, let's say, there are different influence factors. There maybe for a certain period there might be linear, but then they become dormant. So there's kind of this polycyclicity. So there are also a lot of like old scars of thaw slumps, which somewhen occurred hundreds of thousands of years ago, and they are not active anymore because there is no, let's say, trigger mechanism anymore. So often if they're close to water bodies, we have the water that warms the ground, that kind of comes closer, or the coast. We have a lot of thaw slumps on the coast. So, and still, as long as the coast is eroding, then on the top, the thaw slump also gets eroded. So there are a lot of influence factors. Or if there's no more ice in the ground, they typically also, become dormant, let's say.
Okay. I think he was thinking about pattern recognition with that. So yeah, good question. And perhaps we have time for one last question, and then I'd like to ask you about your next campaign in Alaska. What are you targeting? What is the novelty of this new campaign?
So we're kind of doing repeat measurements of our campaign 21. So we're going to Kotzebue, which is in the kind of regional capital of northwestern Alaska. And there we are doing aerial images for structure for motion. So we do 3D models of the land surface. We do multispectral imaging, so in really high resolution, which is 5 to 15, 20 centimeters. We do laser scanning. So we also have a laser scanner to have really high accuracy, high precision measurement of the land surface, because we want to look at also the elevation changes. So in permafrost, we also have, once permafrost thaws, we have a subsidence of the ground. So the ground is sinking. And there are certain areas where that happens more and some where it happens less. And quantifying that is very important. And then now we can do that, have the same type of imagery like in 21 when we went the last time there. So we can map the changes. And of course, and also the beavers. So they're also around there. So we can fly some sites there. But it's a pretty good area for doing research there, because it's super variable. We have a lot of very important field sites as well. So a lot of people also do field work. So we combine remote sensing work with field work to validate our data, to train data, to bring all the different scales together. And the permafrost community is super close and is having a lot of exchange between groups. So people are working together, talking. So it's really collaborative.
And do you have physical models? You didn't talk about this, but I guess for getting the understanding, and if you go to this very high spatial scale, you're targeting a model which explains what's going on, right? Okay.
Yeah, for sure. So there are some groups really focusing on the modeling part. So we have really high definition landscape models, permafrost models, ground that are monitoring the ground temperatures, monitoring different processes that are going on, freezing, thawing, etc. But then there are also these global model people who are doing climate models, where we feed in the, let's say, output products of the remote sensing analysis.
Okay, thank you very much. So I think we have to close. It's 18:15 all the way. So thank you very much, Ingmar. There's this time now to have perhaps a networking with the people in the chat. But then we have to close. Thank you very much, and good luck in the field experiment and all the research plans.
Thank you.
Bye.
Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.